Okay, so think about this for a second. How can something as tiny and delicate as a watch and something as huge and powerful as an engine possibly work based on the same rules? Well, they do. And today, we're going to pull back the curtain and look at the elegant, universal theory that explains how basically everything moves. I mean, just look at the kind of machinery we see every day. On one hand, you've got the mesmerizing, intricate dance of gears inside a mechanical watch. It's like a tiny little city of parts, all working together in perfect, quiet harmony. And then, on the other end of the spectrum, you've got the raw, brute force of a rotary engine. You know, where literal controlled explosions are harnessed to create an incredible amount of power. So you have a whisper-quiet watch and a roaring engine. How in the world are these two things related?
It all just looks like this whirlwind of impossible complexity, right? But what's so cool is that underneath all that apparent chaos, there's a surprising simplicity. It turns out that all machines, big and small, are playing by the exact same rulebook. So let's dive in and uncover the theory that ties them all together.
Okay, so to get started, we need to be on the same page. Let's begin by defining what a machine even is when an engineer talks about one. See, a machine isn't just a random box of parts. It's a system that's been cleverly designed to channel force and motion to get a specific job done. The real magic is in those words, constrained relative motions. You know, think of it like a river. A river has all this incredible power, but it's the riverbanks that direct that power where it needs to go. That's exactly what a machine does with motion.
Every field has its own special language, right? And mechanical design is no different. So to really get how machines work, we've got to learn their alphabet. These simple core pieces that you can combine to build anything from a can opener to a space station.
So the first letter in our new alphabet is the kinematic link. Honestly, the easiest way to think about a link is just as a single, rigid bone in a machine's skeleton. It's any individual part that connects to other parts and is strong enough not to bend or break while it's doing its job. And this diagram here is a perfect example. See each of those numbered pieces, 1, 2, 3, 4, and 5, each one is its own separate link. Now, link 1 is what we call the frame, or the ground. It's the fixed part. All the others are designed to move relative to it, creating this whole interconnected system. Okay, so if links are the bones, then kinematic pairs are the joints that connect them, like your elbow or your knee. A pair is just that point of connection between two links that allows a very specific type of movement, and only that type of movement. A simple hinge on a door, that's a perfect kinematic pair. Now this next idea, degrees of freedom, is absolutely crucial. Seriously, imagine a train on a track. It really only has 1 degree of freedom. It can go forward or it can go backward. That's it. It can't slide sideways or jump up in the air. That constraint is what makes it a train. In machine design, controlling these degrees of freedom is everything. If you have too much freedom, the machine gets all wobbly and imprecise. Too little, and it just jams up and breaks. The entire goal is to design joints that give a part exactly the freedom it needs to do its job, and absolutely nothing more. All right, so now we have our building blocks. We've got links, we've got pairs, and we know about degrees of freedom. So let's see how they come together to create some of the most important mechanisms ever designed. First up is a true legend, the slider crank. This might just be the single most important mechanism ever invented. And even if you've never heard the name, I can guarantee you rely on it pretty much every single day. The absolute genius of the slider crank is how it perfectly translates one kind of motion into a totally different one. See, the crank, that's link 2, it just spins around in a circle, kind of like a bicycle pedal. That spinning pushes the connecting rod, which then forces the piston, link 1, to slide back and forth in a straight line. It's such an elegant way to turn a simple spinning motion into a powerful linear push and pull. And where do we use this? Oh, just about everywhere. This simple design is the absolute powerhouse behind the internal combustion engine in your car, not to mention steam engines and all sorts of industrial compressors. It literally changed the world. Okay, so we know how to control motion. That's half the battle. But what about the other half of the equation? Force. How does a machine make us stronger? Well, the answer lies in a concept that honestly feels a little bit like magic: mechanical advantage. This famous quote from Archimedes, it's not just some poetic line. It's a perfect description of mechanical advantage, this amazing idea that with the right tool, you can take a small effort and amplify it to create a massive result.
So mechanical advantage is basically the number that tells us exactly how much a machine is beefing up our strength. But here's the thing, there's no such thing as a free lunch in physics. To get all that extra force, you have to pay for it somewhere else. It all comes down to a fundamental trade-off.
And here is that trade-off laid out as simply as possible. To get a big output force, you have to apply your small input force over a much larger distance. Just think about using a jack to lift your car. You pump that handle up and down, moving it a huge distance, all to make that super heavy car lift up just a tiny little bit. That is mechanical advantage in action.
All right, so up to this point, we've kind of been looking at perfect machines in a perfect world. But in reality, engineers have to deal with some really powerful, really destructive challenges that want to tear their machines apart.
Unwanted vibration. It's a huge problem in machine design. It makes noise, it wastes energy, and worst of all, it can lead to parts getting tired and just failing catastrophically. Engineers usually think about two types. Free vibration, which is like what happens when you pluck a guitar string and it rings out at its own natural frequency. And then there is forced vibration, which is caused by some continuous input, like an unbalanced engine making your car's rearview mirrors shake like crazy.
So how do you fight this invisible enemy? Well, engineers wage a constant war on vibration. They use complex computer models to predict where it's going to strike. They design in dampers that basically act like shock absorbers for the machine. They meticulously balance every single part that spins. And they build structures that are stiff enough to resist shaking. It really is a battle to keep machines from tearing themselves to pieces.
And there you have it. We've kind of taken the machine apart piece by piece. We started with its basic alphabet of links and pairs. We saw how they build mechanisms like the slider crank. We understood how they can multiply our force. And finally, we got a taste of real-world challenges like vibration that engineers have to overcome every day. So, I'll just leave you with this question. After all this, what machine are you going to see differently now? Because the next time you ride a bike or start your car, or even just open a door with a hinge, I want you to remember that you're not just using an object. You're interacting with the elegant and powerful theory of machines, that silent language that truly shapes our entire world.